Welcome to lecture 61st, and we are going through armature winding, which is more complicated than an AC machine winding. And you recall that to convert it to DC, we have to do these things, that is spatial distribution of polarities of induced voltage existing across each coil. We have taken 16 number of coils for convenience to explain the thing out, and assumed the stator poles to be 4, mind you, P is equal to 4. And this way I did it. I will just tell you that suppose we say that it is a 2 pole machine, 16 coils, how this will look like, so that you understand the previous one much in a better way. So, if it is a 2 pole winding and total number of slots are 16, then I will first calculate coil span, number of coils, number of slots per pole. This is what I have to calculate, slots per pole. That will then become equal to 8, is not? And with the understanding that the start of the coil under north pole, and all the coils are connected in series, of course. So, that thing I quickly do, so that you what will happen if the number of poles is equal to 2, not 4. So, as I told you, all the coils should be connected in series, nothing like that. So, these coils have connected in series. Will there be any circulating current? No, although each coil will become seat of EMF, because if I show the polarities of the voltages, as many plus minus voltages you will see in that series closed thing, so many minus plus you will see, they will cancel each other. So, if it is a 2 pole machine, therefore, I would expect the starting coil sides of say the first 8 coils S 1, S 2, S 3, S 4 up to S 8, they will have a fixed polarity, they will be under north pole. I have taken a snapshot when these 8 coils coil sides, that is S 1 to S 8, S 1 to S 8 coil sides are under say north pole, and direction of rotation is such that polarities of S 1, S 2, if S 1 is plus, F 1 must be minus, because F 1 is the other coil side, must be under south pole. That is how I have made the windings, plus minus, plus minus, plus minus, plus minus, plus minus, and plus minus. And S 9 to S 9 to S 16, these coil sides must be under south pole, coil sides must be under south pole. at this given instant of time, at this given instant. See, coils are moving, but on an average 8 coils will be under knot bolt S 1 S 2. So, it will be like this. Therefore, S 9 to this one, it will be on opposite polarity. It will be like this. Then the next step is series closed. Then from the junctions, I will draw it in a much better manner. What I will do? I will draw a circle. My God. This one I will draw. Now, from the junctions I will bring out some wires, physically connecting it to this one, and this side it will be a thick copper strip. Here there will be a thick copper strips there, like that. And this is how I will complete the diagram. Like this. And here will be another 16 coil sides. And then what I am telling, I will put carbon brushes in space which will be fixed, that will not be rotating. With this armature coils rotating, these copper strips too will rotate in a particular direction. Then I, after drawing these, after taking a snapshot, and this thing with time I am telling you, this distribution of plus minus, this will remain intact. Whoever comes in position of S 1 F 1, after some time S 16 F 16 will come here and S 1 F 1 will advance to that side, but it is destined to have this polarity plus minus. That is the crucial point. Then what I will do? I will put a carbon, 2 carbon brass I will take, which are fixed, where plus plus has come, I will call it B 1, and where minus minus has joined, this is also this carbon brush. It is positioned in such a fashion that this copper strip will be touching this whenever it moves past, and this is a B 1, this is a B 2 carbon brush, and these two I will say this is armature terminal 1 and armature terminal 2, and this time only 2 brushes will do, no 4 brushes required, because you want to maximize voltage. All the EMFs here, no matter which coils, which 8 coils are on the right, which 8 coils are on the left, polarities of the voltages is such that across B 1 B 2 you will always get DC voltage. Got the point. Now, this is fine so far as the understanding is concerned, this is what you have to do. But in a practical DC machine, this type of arrangement it is to be made more solid I mean constructionally. Okay, what is done is this: in the actual DC machine, so brushes are to be placed in proper positions in space. That is, whoever has made the winding, he will tell you, okay, put the brush here, put the brush there, so that you will get DC voltage. In this case, this A 1 become plus voltage, it will give minus voltage. Rotate the armature in that field produced by the stator coils, and you will get DC voltage. So, that is very nice. Now, this one, instead of doing like this, it is to be done in this fashion. These copper strips, in effect, I must tell that these are to be called commutator segments. Okay. These are called commutator segments. Each thick copper strips in this representative diagram, and these are fixed brushes, fixed brush. So, in the armature winding of a DC machine, coils are closed, connected in series. Then you will have two additional things. One is a commutator segments, as many commutator segments as the number of slots, and there will be 2 or 4 brushes or 6 brushes depending upon the number of poles, if the winding is lap winding. That is what I told you. Now, let us see how this commutator segment is to be connected. See, from the junctions you have to drop this one. Now, let us come to this diagram, that is, suppose this is one coil. Let me draw in this developed diagram. This is suppose one coil. I will henceforth show with 2 terminals. It is a multi-turn coil. Okay. Now, what is to be done is this: below this, on the shaft of the machine, this is the shaft. I will put another thing like a ring, which will look like this one. These are copper strips. The one I showed with a circle, it is on the shaft of the machine. I will put it like that. These are called copper strips or called commutator segments. Copper strips conducting. But each copper strip, there will be as many commutator segments as the number of slots, because number of those circular thing we have seen, it is equal to the number of slots. So, those circle thick these lines we draw previously, these I am telling, these are the copper strips. In actual machines it is done like that. Okay. I have not brought that armature winding today, unfortunately, next time I will show you, but this is on the shaft of the machine, it will be inserted. This way it will go, and this is the shaft of the machine, shaft. Got the point? And each commutator segment, adjacent commutator segments should be insulated from each other. They should have their own electrical identity. For example, in the previous diagram, these two are insulated by space. They should not be, if they are touching, purpose will go, very purpose will be lost. Therefore, what happens is this, with a different color I will show. The red portions are called mica insulations, okay? Mica insulations. So that these two, each segment has its own electrical identity. It is not sharing anything with the adjacent commutator segment. They are insulated from each other. Got the idea? Therefore, commutator segment 1, 2, 3 like that 16 commutator segments will be there on a circular cylindrical structure, and each one of them is separated by a layer of mica insulation, and from the shaft also they will be separated, insulated, not that otherwise shaft will become electrically alive, and it will in fact short all the commutator segments, not because shaft is metallic. So, insulations are provided. So, each one with a width like this, then a thin mica insulation, thin, and then another commutator segment. So, it will be the replica of this stator armature like this, it will be the replica of this one here, and it will be shown like this. That is, suppose this is the shaft. In this sectional diagram, what I will do? I can show it like this. Sixteen such 1, 2, 3, each one is commutator segment, these lines are mica insulations like that. So, on the shaft it will be shown over a small radius. So, it will be replica of the rotor two slot arrangement only, but anyway these are all commutator segment 1, 2, 3, 4, 16, got the idea. Okay. So, this is one coil. Then there is another coil like this, second coil is there, I will draw with a different color. Second coil will be in the next slot, it will start from here and it will return from the next slots like this, is it? So, first coil, and this is the second coil, this is the S1 and its return F1. In terms of slots, this is F1 and this is start of second coil, finish of second coil, correct. This is the thing. In terms of slot number, it will be in slot number 1, if S equal to 16, P is equal to 4, then this should be F2 should be in terms of slot number 15 dash, sorry 5 dashed, is not 1 plus 4 number of slots, no for first coil, for first coil. So, it will be 1 5 dashed, 1 5 dashed, and this is 2 6 dashed, and these coils are to be connected in series, that is S 1 F 1. Then I will start with this join S 2 F 2, and this process will continue. It gives you a lap winding. Now, below this I will try to show the commutator segment like this. One commutator segment, also I will number them 2, 3. How many commutator segments will be required? As many slots are there, as many coils are there, because you recall that from the junctions I need one commutator segments. There are 16 coils. So, for each junctions I require a commutator segments. So, this junction I will connect it in commutator segment, suppose 1, that is where is the junction, first coil and second coil. The junction I will drop it to 1, then second coil I will drop it to 2, and so on. Okay. Now, I will go straight away to winding table in its full form, winding table. Slots equal to 16, P is equal to 4, coil span for maximum voltage is equal to 16 by 4 in terms of slots, 4 slots. So, here now I do like this coil, and here I have to do another thing, commutator segments. Two things must be there. Let me try to explain to you. Suppose this is first coil 1 5 dashed. This one I will connect to commutator segment 1. Where coil ends are terminated. It will be in 1, that is 1, I will terminate it, this is the coil, I will terminate it in commutator segment 1, and next one I will its return I will terminate it in commutator segment 2. So, commutator segments I will also numbered 1 to 16. So, 1 and 2, 1 will be terminated here 5 dashed. Next coil 2 6 dashed. This junction I will terminate it in commutator segment 2 and its other end 3, like that. 3 7 dashed. In this way I will carry on. Let us draw the full thing. 5 9 dashed, 6 7 dashed. These are coil ends, mind you, start finish, start finish. 4 I have to add, yeah. 5 9 dashed is okay, 6 10 dashed, is not? 10 dashed. Seven 11 dashed, 8 12 dashed, then another 8 coils are there, 9 13 dashed. Actually, what will happen is this. Anyway, up to this point I will just do, okay. And all these coils are connected in series. And continued like this. So, it is 1 2 2 3, then 3 4 like that. This way I will complete my winding tables up to 16. Next time I will bring the complete diagram in a PDF form, so that I do not have to spend much time. Then what I want to tell is this: there are now several coils connected in this way, that is this is coil 1, each ends are connected in commutator segment 1 and next is 2, its return. Then next coil, from 2 I will start, next coil. So, next coil, first thing is commutator segment 2, this blue one, and its return will be, I will just show this one, it will be terminated in commutator segment 3. So, from the junctions, those vertical lines are coming to the commutator segments, and these commutator segments, because it is connected to shaft, it will also rotate. Then I have to take carbon brushes, which will be not rotating, and they will touch these commutator segments at the appropriate place. That I have indicated how it is to be done after showing the polarities, that I will do next time like this. This will be the brushes touching. So, in this diagram, in this previous diagram, this will be the commutator segment. Your commutator segments will be moving, and you make arrangements so that carbon brushes will touch these commutator segments with the help of some spring and external thing, so that this fellow will rotate, but carbon brush will remain stationary. So, a typical brush will be connected like this at appropriate place, that you have to decide where plus plus sign meets, where minus minus sign meets, negative brush, and then from this armature terminal, say 1 say. So, I will continue this discussion next time, but go through it very carefully. It is so interesting, although complicated, but the analysis of DC machine is much easier. People say construction wise AC machines are simpler, analysis is difficult. In DC machine it is opposite, construction is rather difficult to understand, particularly the armature winding. Field winding is absolutely fine, no complications, but armature winding, there will be slots, there will be armature conductors. Armature conductors are to be terminated on commutator segment, which are mounted on shaft, on the shaft, and there will be fixed carbon brushes, which will be stationary and touching the commutator segment, and placing of the brushes is an intelligent work. I mean, if you put the brushes at wrong positions, you might get 0 voltage as well. So this is how the complication starts, but nonetheless across the brushes you will be ensured about the DC voltage. So, in our next class I will show a complete armature diagram. Lap winding I am discussing only, wave winding I will do a little later, and then two fundamental equations we have to derive. One is, okay, if you know the flux distribution, if you know the number of conductors present in the slots of the armature, then what will be the expression of the induced voltage if the armature is rotated at so much RPM or RPS. That will be the generated voltage equation. How much DC do we expect, on what factors will it depend? And similarly, we have seen that in case of DC machine, for all machines, in case of DC machine as well, whenever generator will supply power, it will experience some electromagnetic torque. When armature will carry current, how much torque will be developed. These fundamental EMF and torque equations, once we derive, then life is rather easier for DC machines. Thank you.